Okay, any questions before we start? Any questions about the capacitance that we defined yesterday, the capacitors, or electric field, Gauss law? If you have any questions, don't wait until next week. I mean, all of you will be asking questions next week, the week before the exam. So if you have questions, ask now. There is no guarantee that you will be able to find me or the assistants next week. Yes?
The homework, after we find the results, there's something like that, expand the results by the power source. Is it similar to Einstein's correction of gravitation?
In a sense, I mean, Einstein has this general relativity theory which predicts how the objects should move, and he predicts that the force, I mean, he says that if the gravitational field is weak, that means in the homework, for example, you are assuming that something is small. If the correction is weak, he says that the gravitational law should be the Newton's constant m over r squared, this is just like Newton, plus some term which is proportional to r cubed, 1 over r cubed. Okay, this is again an expansion in something over r, just like in the homework. You are expanding over the size of the dipole or your system, the separation between the charges, and your observation point. Now, this is something that you do quite common in physics, and most of the time we don't really need exact solutions, exact answers. It's enough for us to test most of the things for a sufficiently high accuracy or high precision.
So the first term is just approximation?
Yes.
The exact result?
The exact result, I mean, the exact result, you cannot really write a force. The exam will be at 1:30, 3 hours. You will have the formula page. I mean, the distribution of the questions will be more or less the same. Half of it just short questions, half of it more involved calculation. You will have at least 10 points of bonus. And the subjects include everything that we will also do next week. So if you have questions, you won't have time to ask it later. Any other questions? Okay, so let's continue with the capacitors. Okay, yesterday we discussed that the capacitance of an object basically measures how much charge you can store in the object. And once you have a capacitor, basically charging the capacitor just means taking some charge from one side to the other side. If you just move plus Q charge from the right-hand side to the left-hand side, you will eventually have this plate negatively charged, this plate will be positively charged. And you are moving charges. Since you are moving charges, you will be doing some work. And the work that you do will be stored as potential energy in the capacitor. So let's first ask the question, what is the energy stored in the capacitor? Now, as usual, we can just imagine we just carry this charging of the capacitor until it is fully charged just by taking small charges from one side to the other side. So let's just imagine we have two parallel plates, a parallel plate capacitor, which is charged with charge Q, plus Q over there, minus Q over there. And let's just assume that we just carry some charge, dQ, from the negative plate to the positive plate. Now, first of all, what is the potential difference between the plus Q and the minus Q plates? Remember, the definition of the capacitance is always this one. So if you know the charge, if you know the capacitance, then the potential difference is always Q over C. Now, if you carry a charge dq from the negative plate to the positive plate, how much work do you do? How much work do you have to do in order to carry this dq charge from this plate to the other plate? Remember the definition of the potential? Which is potential energy change per unit charge. So if you are moving a charge dq, a very small amount of charge, so a potential difference doesn't change when you carry this charge. The change in the potential energy of the system will be just dq times delta V. The change in the potential energy will be just dq times delta V, or q over c times dq. Then, of course, initially the capacitor is not charged. There's no charge in the capacitor, so you just move one dq from this plate to the other one. You don't do any work because there is no potential difference initially. Once you carry the first dq, then the capacitor is now charged, so there will be a small potential difference across the capacitor, and then the successive transfer of the charge dq, you have to do some work, and to calculate the total work that you have done, you just have to sum all the works in each one of these steps. So the total work will be just the sum of these delta u's, which is the sum of q over c dq. But this we can also write as an integral. This is q over c dq. Initially the charge was 0, and finally let's say the charge is capital Q. So this is the total work that we have to do in order to charge a capacitor to a final charge of capital Q. Now if you evaluate the integral, u will be just 1 over 2c q squared, q from 0 to large Q, which is 1 over 2c times q squared. This is the potential energy that we have stored in the capacitor. And this energy is, if you want, you can just extract from the capacitor later on to do whatever you want to do with the capacitor. Any questions on this one? Question? Now, by the way, although we are ignoring the fringing effects, even in this consideration, you see that the fringing effects are important. Mainly because if there are no fringing effects, you can just extract this charge dq from this plate, move it from outside the capacitor to the other plate. If there are no fringing effects, there will be no electric fields. If there are no electric fields, there is no work done. So the fringing effects is what you have to do work against those fringing fields if you are moving the charge dq from this side of the capacitor to the other side of the capacitor. Any questions? Now let's do an exercise. Example. So remember, U is equal to Q squared over 2C. Now we have this parallel plate capacitor. We charge it. So there is a charge Q plus Q over here, minus Q on the other plate. Now let's assume we increase the separation of the plates. What happens to C? Remember, for a parallel plate capacitor, C is epsilon 0 A over L. So if you're increasing L, what happens to the capacitance? It decreases. Okay, so C decreases. What happens to the potential energy stored? Increase. Where did that come from? If energy is conserved. There's no kinetic energy. No, the charges are already transferred to the plates. They are already there. We are not moving charges anymore. So that is how much, this amount of work we had to do, or this much energy is stored already in the system. So after this point, what I'm doing is I'm just increasing the separation. So Q doesn't change after this moment. Somebody else? I always see the same hands. So you can say that energy is not conserved, maybe.
When we increase the distance, actually we are doing above.
Okay, so that is your hypothesis. So your friend has a hypothesis. He says that if you want to separate the plates, you have to be exerting force on the plates. But if you are exerting force on the plates to move them, then you are doing work on the system, and that is what increases the potential energy. So let's check his hypothesis. So what should be the, let's just, for simplicity, let's assume that we keep this plate fixed, we move the other plate. Very slowly. I mean, it doesn't gain kinetic energy, let's say. How much force should we exert on it? On this plate to be able to move this plate? What is the electric field inside this plate? Let's say the area is A, the separation is L, the charge is Q. What is the electric field created by infinite parallel plates of charge density sigma? Sigma over epsilon 0. What is sigma? It's the charge per unit area, Q over epsilon 0A. So this is the magnitude of the electric field. So how much force does this electric field exert on this plate? What is the force? Force will be electric field times the charge. So this will be Q squared over epsilon 0A. This is the force that you exert. Now, we have these plates. We are separating them. As the separation change, does the force change? Does the force depend on the separation between the plates? No, there's no L dependence. So this is just a constant force. Now, this is the force that each plate is exerting on each other. This is not the force that we are exerting. But if we want to keep the plates fixed, we have to exert such a force, because if the force acting on a plate is non-zero, it will accelerate. So the separation will not be constant. So we should be exerting this much force anyway to be able to keep the plates in their place. If you want to separate it even further, you have to exert a force very slightly larger, negligibly larger than this one. But we can say that the force that we are exerting on the plates should be equal to this one. So it's a constant force. What about the work done by a constant force? It's just force times the displacement. So this is Q squared over epsilon 0A, let's say the final length minus the initial length. So this is the work done by us on the capacitor. Now let's look at what is the change in the potential energy of the capacitor. Remember, the potential energy was Q squared over 2C. And if you just substitute the definition of C, this is twice epsilon 0 A over L, or Q squared L over 2 epsilon 0 A. Right? Yes. So you see, this is the force exerted by the plates on each other. We are exerting a force on this direction and displacing it in this direction. So we are doing positive work on the system. Let's say infinitesimally small. And eventually we take the limit that difference goes to 0. So we are not causing the charge, the plate to accelerate. It moves at 0 kinetic energy, in a sense. So this is the change in this one, and delta U is equal to Q squared over 2 epsilon 0 A delta L. Compare with W is equal to Q squared over epsilon 0 A times delta L. This factor of 2. There is this factor of 2 difference. So either his hypothesis was wrong, but if his hypothesis was wrong, it means that energy is not conserved. I mean, that is not something we want. So we did something, or we did something wrong. So what is our mistake? There is a mistake in one of these lines. Okay, let's just add a minus sign, but that doesn't get rid of this factor of 2. It will make things even worse. We would like to have the work, if we have energy conservation, the work that we have done should be equal to the change in the potential energy. If this is not satisfied, then you cannot talk about energy conservation. Yes, that's our assumption. We imagine, just to test his hypothesis, we imagine that we fix one of the plates. We have to exert a force to fix it. But since it is fixed, it's not moving, that force doesn't do any work. And we are exerting another force on the other plate and move it from an initial LE to a final LF separation. And we say that this is the work done by the force that we apply, and this is the change in the potential energy. So what is wrong? Let's go step by step. Is the potential energy equal to Q squared over 2C? And that is what we derived in a moment ago. So it's supposed to be true. C is epsilon 0 A over L. So there doesn't seem to be anything that goes wrong with you. Let's go before. Is this the electric field? Why 2 epsilon 0? No, this is correct, by the way. The electric field in between these plates is sigma over epsilon 0. There's no 2 over there. But there is a 2. Why? So we are calculating the force acting on this minus Q plate, remember. So what exerts the force on this minus Q plate? Only the plus Q plate. What is the electric field created by the plus Q plate only? Remember, this sigma over epsilon 0 electric field is the sum of the electric fields created by the plus plate and the minus plate. But only the plus Q plate is exerting a force on the minus Q plate. And the electric field created by the plus Q plate at the position of this minus Q plate, let's just denote it by E plus, it is sigma over 2 epsilon 0. So F acting on the plus plate will be equal to the minus plate. The electric field created by the plus plate at the position of the minus plate multiplied by the charge. So here we have our factor of 2. energy conservation is saved. Okay, this is one thing that you have to pay attention to whenever you are talking about the force is equal to electric field times the charge. The electric field is always the electric field created by other charges. It's not the total electric field, it is the electric field created by the other charges that exerts a force on a given charge. Now, any questions on this energy stored in a capacitor? So this is the electric field. Now this is the energy, which, by the way, we can also write as Q over C times Q. And Q over C is delta V, 1 over 2 Q delta V, or you can also say 1 over 2 C delta V squared. If you just replace Q by C times delta V, this is the final expression you obtain. So all of these expressions are valid. Now let's express everything in terms of the electric field. So U is equal to 1 over 2. What is the capacitance of a capacitor, of a parallel plate capacitor? Epsilon 0 A over L. This is C. Delta V in terms of the electric field, E dot dl, electric field is constant, so it is E times L. This is delta V squared. This is equal to 1 over 2 epsilon 0 E squared times A times L. So this is the total energy stored in a parallel plate capacitor of area A and thickness L. Well, here there is an interesting combination. What is A times L? You see, the capacitor, as we imagine, let's say a disk of area A, it has a height L. So this is just the volume. So the U is 1 over 2 epsilon 0 E squared times the volume, where the electric field is non-zero. So it's the volume of the capacitor, but also inside the capacitor the electric field is non-zero. Outside, everywhere, the electric field is zero. Well, currently it just looks like a coincidence. Let's see if we can obtain such a relation for some other capacitor. So what other capacitors did we study? We had the spherical, we had the cylindrical. Let's do the spherical capacitor. What is the capacitance? Do you remember? Four pi epsilon 0 and R. No. R1, R2 over R1 minus R2. That's spherical, just I have two spheres. Well, if you don't remember, I can never remember such things. Let's just calculate it. And let's review how we calculate the capacitance. Now we are imagining these two spheres, one inside the other one. The outer sphere has radius R1, the inner sphere has radius R2. And we imagine putting some charge in the inner one and so the minus Q charge on the outer one. So this is basically, whatever the system is, this is how you check for the capacitance. So we put the charges. The next thing, we have to evaluate the potential difference between these two conductors. And once we obtain that potential difference, then C will be just Q over delta V, where delta V is the potential difference. To calculate the potential difference, we have to determine the electric field first. Well, the electric field here, at this point, let's say, this point is inside the outer sphere, so there is no electric field. There is no contribution to the electric field from the outer shell. The only contribution is from the inner shell, and the inner shell just acts like a point charge. So the electric field magnitude will be 1 over 4 pi epsilon 0, 1 over r squared. And the potential difference will be just E dot dl from R1 to R2. And this will be 1 over 4 pi epsilon 0, 1 over R2 minus 1 over R1. Or delta V is equal to 1 over 4 pi epsilon 0 times Q times R1 minus R2 divided by R1 times R2. This is my delta V. Well, I know delta V, so I just put it over here, and then that gives you the capacitance. C is equal to 4 pi epsilon 0 R1 R2 over R1 minus R2. Now, what initially your friend was saying, just 4 pi epsilon r, was, now what happens if we imagine that this outer sphere has infinite radius? So it's just the boundary is at infinity, so we don't see it, it doesn't have any effect, etc. You can still define the capacitance C for an isolated sphere. Just imagine, just a sphere itself, you can still store charge on it. It creates a potential difference between infinity and the surface of the charge. And so you can define a capacitance as the Q is equal to the capacitance of the sphere times the potential difference between infinity and your charge. Or you can just take the previous result, C is equal to the limit as R1 goes to infinity, 4 pi epsilon 0, R1, R2 divided by R1 minus R2. This is 4 pi epsilon 0, R2. Now, although most of the time we think of a capacitor as a two-conductor system, if one is charged plus Q, the other one should be minus Q. An isolated conductor, you can still treat it as a capacitor, understanding that the second conductor is at infinity. So now we know the capacitance of this sphere, of these two spherical shells. We can calculate the energy, 1 over 2 C times delta V squared, which is equal to, or let's say rather than this one, Q squared over 2C. This is equal to Q squared over 2. Well, 1 over C is R1 minus R2 divided by R1 times R2 times 1 over 4 pi epsilon 0. Which is 1 over 4 pi epsilon 0 times Q squared times 1 over R1 minus 1 over R2, or let's just leave it as R1 minus R2. Now, of course, this doesn't look like the electric field times the 1 over 2 times the electric field squared times epsilon times the volume. But, I mean, the difference of this example from the parallel plate example is that in the parallel plate example, the electric field was just uniform everywhere. Here, the electric field is not uniform. But we can make one approximation. That is R1 minus R2, let's just call this dr. This is small. Very, very small, very thin layer. If you want a thick layer, you can just consider the thick layer as the sum of very thin layers. Now, if this is the case, R1 is almost approximately equal to R2 anyway. So let's just call it R. Now the electric field, no, not the electric field, this is the potential energy stored. This is equal to 1 over 2 times 1 over 4 pi epsilon 0 q squared over r squared times dr. Well, still not that nice. You see, the electric field depends on Q only, not Q squared. So this will be equal to 1 over 2 times 1 over 4 pi epsilon 0 Q over R squared, everything squared. So I get this Q squared. Then, of course, I also get other factors, 4 pi R squared dr epsilon 0. Now this line and this line, they are equal to each other. Now the reason why I did this trick was here now I have the electric field in my very thin shell. So this is again I am imagining this very thin shell. So the potential energy stored in this capacitor made by this very thin shell is just 1 over 2 epsilon 0 times E squared. This is this term over here. Well, 4 pi r squared is nothing but the surface area of my thin shell, and dr is the thickness of my thin shell. So this is the volume of my shell. And again, we have the volume where E is non-zero. Whatever capacitor you can think of. In fact, you can even think of a capacitor in which the conductors, one conductor is at infinity over there, the other conductor is at infinity over here. So there's no conductors, you only have the electric field. Energy of the system will be always as 1 over 2 epsilon 0 E squared sum over all the volume. So what we do is we identify this expression this is the energy density stored in the electric field. So initially when we started talking about the potential energy of a given charge distribution, we always were talking about the potential energy of the charges. So you bring one charge, you are doing work against the charge to do some work. So we were always discussing as if the potential energy was a property of the charges itself. But this derivation tells us that we can also talk about the potential energy as a property of the electric field itself rather than the charges. So when you are bringing one charge, let's say from minus infinity, you have to do work, and the reason why you have to do work is that you are changing the electric field. And if you are changing the electric field, you are changing the energy density stored in the electric field, and hence you are changing the total energy stored in the electric field, and hence you have to do some work if you want to conserve energy. So this is, in a sense, a different way of looking at the energy. Energy is not stored in the charges. The electric energy is stored in the electric field itself. So this is one of the properties of, if you remember the first time when we defined the electric field, we said that for the time being, it is just a mathematical object, a mathematical tool that we invented. But now we see that that mathematical tool actually carries energy. So it has energy. Well, since currently we are only looking at electrostatics, the energy is fixed. But when we study electrodynamics, we will see that this energy is also flowing. But momentum is nothing but the flow of energy. If you consider point objects, they have a momentum if they are moving, but if they are moving, the energy corresponding to them is moving also. So momentum is in fact just the flow of energy. Now, if the electric field is changing, we will see later on that it corresponds to a momentum. And the electric field will also have a momentum, not just energy, but a momentum also. But for the time being, it's just the energy. It has an energy. It's not just a mathematical tool that we invent. It is something that carries energy.
Why did we consider the sun?
The sum. Well, energy density, what you mean by energy, well, let me also say delta V. Energy density is just like the mass density. It is the mass per unit volume. So if you have electric field everywhere, what you need to do is you just imagine small volumes filling up everything. In each one of these small volumes, there is an electric field, and that electric field corresponds to an energy density at that point. And the energy in that very small volume is just the energy density times the volume. Well, this delta V is the volume, by the way. This is not the change in the potential. Or let me write it in this form. A very small volume element. So let's say we have this region where electric field is non-zero. Well, this region can be infinite. And it doesn't have to be finite. What you have to do to calculate the total energy stored in this electric field, divide it into very small volumes. Etc. Each one delta V. At that point, there is a potential energy, or energy stored in the electric field, and the energy in that very small volume is U epsilon times delta V. The total potential energy is just the sum of these delta U's, UE times delta V.
4 by R squared, dr is the total volume. It's not a volume.
Well, you see, in this example, what we did was we have these two very thin shells. So the volume of this very thin shell is equal to 4 pi r squared dr. Now, since it's already a very thin shell and the density is uniform over there, we don't need to divide it into more pieces. So basically, in this sum, in this example, there's just one term in this sum.
So this is the general.
This is the general expression, whatever the system is. If you have a region where there is an electric field, the energy stored in the electric field is given by this expression. Whatever the system is. We only saw it for two special systems, but in general, for any system that you can imagine, this is valid.
How can we say that energy is carried by the electric field or stored in the electric field physically?
This one? I mean, what do you mean?
The intuition into potential energy stored in electric field.
Now, you see, have you ever seen these the glass? I mean, they are kind of toys. They are closed, but you can see through, and there are just 4 flaps inside. And when you shine light on them, they start to spin. So they will just basically look like this. They're closed in glass. So inside there is a very thin wire. On the wire you have these objects. And one side of these things are dark. The other side is white. One side is dark. When you shine light, this object starts rotating. Even in vacuum. If it's not in vacuum, then things get a bit complicated, but in vacuum it just rotates. So light kind of exerts pressure. It exerts force, which means it's exerting a pressure, but force is nothing but a carrier of energy. If you are exerting a force on a moving object, you are transferring energy to it. So light has to carry energy. Light is nothing but a collection of electric and magnetic fields. So this is our first statement, that electric fields contain energy. Of course, we will proceed and we will study the magnetic field, the energy stored in the magnetic field, and how they carry momentum and energy. That we will eventually come towards the end of the semester. For the time being, this is our, let's say, first step to understand this phenomenon.
This means that energy is carried by the electromagnetic waves in the electric field.
Yes. Well, sound is a different thing. I mean, sound is just the vibration of the atmosphere. Well, we will be studying what happens to the electric field in medium. We will study that, but not yet. And we will see that there are, as you said, there are some phenomena which will influence the electric field. The behavior of the electric field in medium will be different. You see, what happens is light transfers more momentum to the white. So the white just moves backward. If you just shine light from here in this direction, this will just reflect it back. So if there is more momentum transfer on this one, so this will be rotating like this. In vacuum, I repeat. If you go to a toy shop, find this toy, and do this experiment, you will see that it rotates in the opposite direction, because they are not in vacuum. Other questions on the electric field, the energy stored in the electric field, the energy stored in the capacitor. Now in the next hour, for example, we will start to discuss what happens if you put some insulator in between these parallel plates. So that will be our first step to answer your question. Awesome. So see you after the break.